Okay, today we're going to have a look at an equilibrium system that's being established between iron 3 plus and thiocyanate ions to generate a complex ion of iron thiocyanate. Now the iron thiocyanate is a deep blood red colour, and if we have a look at our iron, it's sort of a yellowy brown, and our thiocyanate is a clear colour solution. So if we add these two together, we'll establish an equilibrium system. Okay, so we'll produce the same blood red colour. Now I'm going to add a small amount of this to our spotting tile. Okay, what we're going to do today is see if we can shift this equilibrium system in the forward and the reverse direction by changing some of the concentrations of the ions that are present. So in the first one, we're going to add some ferric chloride, some iron chloride. Give that a bit of a stir. And it's difficult to see, but you might be able to pick up that the colour intensity for this one has increased. It's a darker red solution. In terms of the equation, if we're having a look at what's happening here, we're increasing the concentration of iron 3 plus. Right, and this is what you can see as this sudden spike in the concentration of iron 3 plus in the first graph. This will place a stress on the system at equilibrium. According to Le Chatelier's principle, the system will counteract this stress. So it's going to shift the position of equilibrium to the right. Now in doing so, we should then see, as a consequence after this reaction, a decrease in the concentration of the iron 3 plus, and we do. We should see a decrease in the concentration of the thiocyanate ion, and we should see an increase in our complex, our iron thiocyanate. Okay, so we should see an increase in that blood red colour, and we do in that one. Alright, in the second graph we're going to change a different quantity now. So for the second one, we're going to add some ammonium chloride, and we'll see what happens. Right, so I'm just adding a few rice grains of the ammonium chloride. Give it a bit of a stir. And we'll find this time it's not quite shifting all the way back, but the intensity of that red has diminished. So in this one, we're shifting the position of equilibrium, it appears, more towards the yellow-brown side and away from the blood red side. Now, by adding ammonium chloride, what's reacting in here is the chloride ions, and the chloride ions are combining with some of the iron 3 plus to give us FeCl4 minus, and effectively what that's doing is lowering the concentration of Fe3 plus. Once again, this is placing a stress on the system at equilibrium. The system will counteract this stress. If we're removing Fe3 plus, the system will try to produce some more Fe3 plus. So in doing so, it will have to shift the position of equilibrium to the left. If that's going to occur, then the concentration of FeSCN2+ must decrease, SCN- should increase, and then Fe3+ should increase again. Now the difficult part is representing this on a graph. We've got this second graph. We can see the system has been shown as a system that's at equilibrium because all of the lines are parallel, the slope is 0. The concentration for these quantities is not changing with time. And then we can introduce our change. We can suddenly decrease the concentration in iron 3+. The system's response was to slowly generate some more. If we're generating some more, then we'll also be generating some more for the thiocyanate ion, and this time our iron thiocyanate will be decreasing. Does the system reach a point of equilibrium again? Well, yes, we've got a point where the lines are parallel again, the concentrations are not changing with time, the system has re-established equilibrium. Right, for the third trial, we're going to add some potassium thiocyanate. Once again, a number of rice grains, and it's difficult to see, but compared to the last one, it's similar to the first. We have an increase in intensity of that blood red colour. So our third test appears to be shifting the position of equilibrium to the right again. Now, if we consider what we're changing this time, it's going to be a bit crowded here, but we're increasing the concentration of thiocyanate ions. This is placing a stress on the system at equilibrium. The system will counteract this stress by shifting the position of equilibrium to the right. And in doing so, we should see a decrease in the iron 3+, then a decrease in the thiocyanate, and an increase in the iron thiocyanate. So we can represent that on our graph as well. So initially our change was an increase in the concentration of thiocyanate, and then to follow it should decrease. In doing so, the iron 3+ should also be decreasing, and our iron thiocyanate should be increasing. Does the system reach a point of equilibrium again? Well, those lines once again become parallel, which indicates to us that as time is proceeding, the concentration of these quantities is not changing with time. The system has reached that point of equilibrium. All right, for the final trial, we're going to add some potassium iodide. All right, so for this one, we're going to add Ki. Now, in the potassium iodide, we have the iodide ions, and these are a reducing agent. I'll add a small amount. This one's a little bit more immediate. A few rice grains. And with trial 2, I think we added a bit more in trial 2. This is more what we'd be looking for in the shift. This is a definite shift. We've got that yellow-brown colour being produced. So for the fourth trial, we are definitely shifting the position of equilibrium to the left. We're reducing the concentration of the FeSCN2+, so we're losing some of that blood red colour, and we're producing that yellow-brown colour. Now, for this graph, I'm not going to draw this one, and I'm not going to explain any further than the iodide is a reducing agent. For this graph, I want you to go away, see if you can investigate what's happening. If I give you the hint that it is the iodide ions that are making the change this time, and given the evidence that the equilibrium is definitely shifting position to the left. See if you can work out what's going on, and see if you can draw and complete the final graph for this equilibrium system.